Okay, so this is the third question of the Physics 101 final in spring 2018 semester, where we are asked to consider a yo-yo which is tied to a string and it's falling down. The first thing we have to calculate the angular acceleration of the disk. Let's look at the free body diagram. What are the forces acting on this yo-yo? There is the weight, mg, and there is the tension in the rope, which is T. So I can quickly say that this is going to fall down with some acceleration a. M times a must be mg minus T. But this is a solid object, which means it also has an angular acceleration. What would be the I times alpha? What would be moment of inertia times angular acceleration? That would be the total torque. And according to center of mass, the total torque is just T times R. And I is given as 1/2 mr squared, so I have m r squared over 2. Alpha is T times R. R is cancelled. mr alpha is over 2 is equal to T. Now I have T as an unknown, alpha as an unknown, A as an unknown. So 3 unknowns, 2 equations. That's not enough to solve. But alpha and A are not completely free, right? As this thing falls down, it must rotate so that new rope becomes available to fall down. This is like rolling without slipping. Alpha is A over R, or I can maybe write A as R alpha. So let's plug this in here. I have M R alpha equals mg minus T. The other equation is m r over 2 alpha is T. If I add these up, I find 3 over 2 m r alpha is mg, m's cancel. So alpha we find 2/3 of g over r, which is kind of makes sense. G is meters per second, so R is meters, so this is 1 over second. It's less than G. A apparently is R times alpha, so 2/3 dg. So acceleration is slower compared to a free-falling object, which is what we expect. Calculate the time it takes for center of mass to fall a distance. So this was part A, we've done it. How much time does it take for the center of mass to fall a distance h? Well, this is motion with constant acceleration. So T will be 2h divided by h square root. A I have already calculated, will be 2 times h times 2 over 3g. So it's going to be 3h over g. Okay. Calculate the angular velocity of the disk when it has fallen by a height h using our results in A and B. Well, angular velocity of the disk, omega, will be just alpha times t. Initially it was not rotating. Alpha we find as 2/3 g over r. T we found as 3h over g. So let's put everything into a big square root. And this is going to be g squared over r squared, so g is cancelled. So what do I find? I find 2 is outside g h over r squared, which is nice, right? How about part D? What does this ask? Calculate the angular velocity of this when it has fallen by a height h using energy conservation. So if I actually fall by a height h, so this is my initial position, the initial potential energy mgh must be converted into 1/2 m v squared plus 1/2 I omega squared. Now, these are the same m, so let's write them carefully. I we are already given as m r squared over 2. So now m is cancelled. It's nice. And then what do I know? I know the following. V must be R times omega. So if this is V, right, omega must be V over R. So GH is 1/2. V is R times omega, so I have R square omega square plus 1/2 R square omega square. Overall, it's going to be 3/4 R square omega squared. GH omega is 2 square root of GH over 3 R square. Let's check if we have the same result. Yes, we have the same result, but in the previous one we have forgotten a 3. So it's nice. We got the same answer using both ways, so most probably we have actually found the correct answer.